So our first, I think the first line is transistors to logic gates, right? I think the course is I think it's a microprocessors and interfacing, microprocessing and yeah, micro interfacing. So what I decided to do is that I decided to take a typical MCU microcontroller unit that has a microcontroller and then please keep quiet. It has a microcontroller and then it has some interfaces, right? So the first few lectures were about the microcontroller and then those interfaces. I showed you to actually program the microcontroller and then look at the interfaces, the UART interface, the serial interfaces, and stuff like that, right? So that is the on the interfaces. Now you're going to the microprocessor itself. So what is inside the microprocessor? That's what you're going to study. And then I'm going to make it as easy as possible for you guys. Once you pay attention, it will be easy. But if you don't pay attention to it, then it will be difficult. But since some of you have done the assignment already, I think it will be easy for you guys. Or you guys just saw the answers somewhere and just copy them. So here all we are going to do is you have to tune your mind to thinking in zeros and ones, right? High voltage, low voltage, zero ones. That's all you're going to, that's how you can understand this section of the course, right? Zeros and ones, just think about zeros and ones. And if I give you a number, you should be able to easily convert that number to binary number, right? So once you understand that, then you'll be okay. So now this is how a typical single cycle microprocessor looks like inside the chip, right, of your single cycle microprocessor. This is how it looks like, right? You have a component called the memory. You guys already know what memory is. You have a component called the register file, right? You have a component called the ALU. Here you have two memories. There is an explanation for why there are two memories. Some have only one memory within the microprocessor, not the entire, not your entire computer, just only the microprocessor. You have some memory inside there. You have register file. The register file is also a type of memory. And then you have the ALU, the arithmetic logic units inside there. And then I gave you an assignment on the ALU and for you to draw the architecture of the ALU. And some of you have done it already. So 100%, right? So this is how it looks like. So at the end of the entire course, you should be able to know the architecture of each of these components, right? So now, but even from the high level point of view, right? How does a code like this work on your CPUs, right? If you write, so you know what this code is. What is this code? Is it C plus plus? Is it C plus plus? And man, STDI. This is C code, typical C code, right? Simple, a very simple C code that is in the code. So if, pardon? So this is a typical C code, right? And then how does this C code work? And then how will your computer interpret this C code, right? That is what that's what that's what your CPU do. It takes this high level. So once you are writing, what you normally do in programming is that you want to talk to the hardware. The hardware only understands zeros and ones. We call it machine language. It understands only machine, and then those machine language, the hardware is made up of the basic component of the hardware is transistors. So the transistors only understand a logic one. A logic one means that you've applied some voltage to it, and then it understands logic zero. A logic zero means there's no voltage applied to it, right? So that's what the hardware understands. So how do you talk to the hardware, right? if you're using zeros and ones, and then humans, you can also program in zeros and ones. At first, they did that, like they program in zeros and ones, like zero zero zero. Those numbers mean something, but it's difficult to do, right? So now you need a high level language to be able to talk to your PC, right? So that high level language is like C, it's like C++, it's like Java and stuff like that. So you use those high level languages, you program in high level languages, but the PC don't really understand what you are doing once you program in this language. So there are some steps that this code you've written, this high level language you've written, must go through before your CPU can understand it, right? But you guys have actually learned some kind of language before, any programming language, right? You guys have never learned any programming language before. Yeah, yeah. But I mean, I left on go, but it doesn't. It's still the same procedure, right? But then, but then, you forgot. Yeah, of course. But I mean, so you know that this code, what this code will do is that you write this code using an editor, and then what you do is that you have some kind of IDE that will compile this code into a form of language that the machine can understand, right? So you have what is called a compiler. You guys have heard it before. You know, I know once you've done coding, you've heard compiler before, right? So your compiler takes this high level code, very high level. It's high level because you can understand it, right? You can understand that print every just an English print something. Then what are you printing inside there? You are printing hello world. So you can understand it. So it's a very high level language. So the compiler takes this high level language, and then it breaks this high level language down into an assembler, into assembly language. The assembly language is the language of the CPU. Now, this is not the basic level yet, right? So you have your compiler, and then the compiler will break this code down into an assembly language, right? And then you take an assembler, another tool that will break this assembly language down into your machine code. So your machine code are the zeros and ones that your CPU can understand. Understood? That's easy, right? Do you understand? So now this is how it does it. So from your high level language to the machine code, right, you take a typical C. You have int x is equals to 10. Then you have x is equals to 2 plus x plus 15. This is a very simple code that will double x and add 15 to x and store the value in x. Simple C code, right? Now what happens is that what it doubles x, the 10. You know x is equal to 10 from the beginning. So it doubles x and add 15 and store the value back in x. Store it back in x. Right. So now you take the compiler, and then the compiler will compile this code into an assembly language. Right. Now each CPU designed by whoever designs their own CPU has a language that they use for their CPU. Now, the ones we saw here, the components we saw here, every CPU has them, but every CPU arranges them in a different way, right? Every CPU is looking for something else. Every CPU is looking to optimize something, right? So if you take CPUs from Intel or something, they have a different language that their CPUs can understand. So once your compiler should be able to compile that code into the assembly language that your CPU understands. Each CPU and its own assembly language. Understood? Right. So now here we are going to be looking at a new assembly language called the RISC-V assembly language. It's a new assembly language developed, I think, about 12 years ago or something like that. So it's fairly new as compared to the ones developed by Intel and stuff like that, right? It was developed in university by students and then their professor, right? But now it has become a very high standard assembly code that a lot of industries use. right? So that's what we're going to be studying. So now the compiler will compile this one into your Wix 5 assembly language. And then this is how the assembly language looks like. Have you seen it? We have, so this code here, this entire code here will be converted to this. So if you understand assembly language, you know that this code is doing exactly this, right? This assembly language is still human readable. You can still understand what it's doing. You can see that you have something like add I, even though probably you understand what add I, but you add, it's adding something. So it's adding what? You have three variables here, R5, R0, 10. And then we said that the int x is equal to 10. So it means that you have a value, a constant value 10 that is stored in x, right? So the first assembly language will do what it does is that these are what are known as registers. So R0, R5 are registers. Then this 10 is a constant, right? Have you seen it? Now in Rex 5, there are a number of registers. So here, each CPU has a register file. It's called a register file. So in the Rex 5, we have a number of registers in the register file. Where is that? So we have a number of register. So we have the register file, right? Register file. And then within the register file, we have a number of registers inside there. And then the registers are labeled R0, R1, up to R31. So it means that we have 31 registers inside the register file. Understood? Right? And then this register, R0, is always stores constant 0. So a 0 value is stored here. The rest of them don't store anybody. You can write to them and read from them. But this R0 here stores the constant 0. So R0 is equal to 0. Understood? So what we have done here is that once you see a code like this, add I, R5, R010, one register is known as the destination register, right? One register is also known as the source register. So here R0 is the source register. And then what this code does is that it does R0 plus 10 is equal to R5. Understood? So R5 is the destination register, R0 is the source register. So, and I said R0 always stores the value 0. So if I have from the top int x is equal to 10, and I want to store that value somewhere, all I have to do is R0 plus 10 will be stored in R5, and then I've done that. I've done that. So the compiler has compiled that code into the assembly language. Understood? And then the rest follows. You can go through the rest and see, but you'll learn it later on also. Understood? Do you understand? So after that, we have an assembler that will convert the assembly language into the machine language. So this is the machine language. You see that there are three lines of code, right, in the assembly language. So the next one, the assembler will convert this one into the ones and zeros. So each, even though you see them as just zero, stuff like that, but each field means something. Each letter they means something. Understood? Right. So, for instance, if we take the entire thing, this entire code, right? So these codes are what your CPU runs. So these codes are always stored in your memory, and then your CPU runs them one at a time. It reads the memory and then it checks it checks what the code is, and then it runs it, right? So what this code is doing, that just take the first time. This entire code is 32 bits, right? 32 bits. So if you count them, they have to 32 bits, right? And then we always break the bits, the 32 bits into what is called the fields, right? So the first, I think 7 fields here, the first 7. So in case you are giving any machine code like this, and then you are giving, you'll be told that, oh, this is a Rex 5 machine code. You must understand that the first 7 bits are always what is called the opcode, the operational code, right? Operational code. So here, the opcode for the CPU does a lot of things. It can add, it can subtract, it can multiply, right? So the opcode is the operation that the CPU is doing, or that kind of, or that line of code is doing, right? So if I have this opcode means that I'm doing add, right? The next field is known as the destination register field. So you see that this is R5. So if you see 00101, so 101 in decimal is what 5. So I said you must be able to convert numbers between decimal and binary. If you don't know how to do that, this will be very difficult. But if once you know how to do that, it becomes easy, right? So this is destination register. So R5. So this is why this is why. And then this is another field called the function. We will let that later. And then this is R0, this is the sort register. So you see that R0 is 00000. R0. I said R0 means register 0. Right? And then this is the constant value. Are you seeing this one? So if you see something like 00010101010 is 10 in binary, in decimal. So that's what the code does. So it's not actually random. It's actually being, or each field means something. Understood? And then that's what we're going to learn. Do you understand? Should I continue? Should I continue? So all you are doing is that all that assembly, that machine code is stored in this memory over here, right? It's stored in this memory, and then you read the memory one at a time. So it's 32 bits, as I said. So it will read this 32 bits value. It goes through some kind of control. So the control will determine what operation it is, right? Whether it's addition, whether it's subtraction. And then, as I said, we have register files, and then it will give the values to register files or ALU or whatever, right? So that's what happens within your CPU. Do you understand? Do you guys understand? Okay, so now we have something called the ISA. So the what we saw, the assembly language is like some kind of ISA. It's called instruction set architecture. Each CPU has its own ISA. And then what the ISA we are going to be studying is the RISC-V ISA. So the ISA is just like an interface between your software, the software code you write, and then the hardware, right? Like how the assembly language we saw is like it's just like the ISA. It's just an interface between the software and the hardware, right? So it helps you talk to your hardware by writing high-level software languages. Understood? Right? So now, if we take in any computing system, like we normally have the computation unit, we normally have the communication unit, and then we normally have the memory and then the storage. I think I've already explained this before, and then I said that the the computing unit could be your CPU, and then right now we have some specialized kind of units known as FPGAs. We have some known as ASICs and stuff like that. That one is not important, but from what the basic thing is that the computing unit would would normally be your CPU, right? Now you have your communication units. You have some kind of link between your memory and then your computing unit, because what your CPU is doing is that it is reading instructions from your memory and it is executing those instructions, right? So you need some kind of link, and then that link is the communication unit. Then we normally have memory and storage. You know the difference between memory and storage. Memory is the on-chip memory. So if you take your CPU, if you take the chip of your CPU, there's some kind of memory inside, and then you always your laptops also have some kind of a hard disk, right? the hard disk will be the storage. Understood? Right. So here, so all the processor is doing is that the processor is reading something or is reading an instruction from the memory and then it is executing that instruction. And then based on the architecture of your CPU, right? Or based on how your CPU is arranged, we have different forms of architecture. We have one called the von Neumann. Have you guys ever heard of it before? Von Neumann architecture or the Harvard architecture? No. Okay, so we have we have essentially two types of CPUs. We have the von Neumann architecture CPU, and then we have the Harvard architecture CPU, right? Now, as I said, once you write your code, like you wrote the, once you wrote that code, the end, x is equals to 10, x is equals to 10 plus, whatever. Once you write something like this, right? Now, this code will be compiled into your assembly language, and then your assembly language will have instructions. We have a part for instruction, right? And then you have a part for data, right? So here, once you write a code like this, the instruction will be the one we saw, the add I. Add I is an instruction, right? Your data is the 10, right? This is a constant. X is equal to 10. It means that you've created a memory and then you've stored 10 in it. It's a constant, right? So now, once you have instructions and data, how you store your instructions and data will determine the type of CPU you are using, right? So if you take the von Neumann architecture, what it does is that it stores, it has only one memory, like this, where it stores both instruction and data. So instruction and data is stored in one memory, right? And then you have your CPU here. So your CPU reads both data and instruction from one memory, right? So now it means that your CPU can actually read from one memory address at a time. So what if you want to read both instructions and data at the same time? So it means that with this kind of architecture, it's impossible, right? Because there's only one link between the CPU and the memory, and then we have both instructions and data inside it. So you can only read one at a time, an instruction at a time, or data at a time. So what if you want to read both instructions and data? So we have another architecture called the Harvard architecture. Harvard, right? So that one, it takes two memories. So you have your instruction memory, and then you have your data memory, right? And then you have your CPU here, which connects to both your instruction memory and then your data memory, right? So here you can actually read from two memories at a time, but sometimes it's a waste of memory because if this memory is not filled up, then it means that you have wasted memory, right? So all of them have some kind of drawbacks, right? So these are the two types of architectures in computing. Understood? So here, so here you have your software on top. Your software has an, or your CPU has an operating system, and then the applications you write run on your operating system. Your operating system has the compilers and stuff like that. And then in between, in between your applications and then your hardware, right, is the instruction set architecture, as I said. So essentially, what you're going to be studying is the hardware. And then in the hardware, you know that the hardware is made up of transistors. We are not going to go into that. That is a different course. I think semiconductors or something like that. Right? So, but we are going to say a little bit about logic gates. So you have to know how to use the transistors to make logic gates. Right? You use transistors to make logic gates, and then you have your ISA on top. So that's what you're going to say, the ISA, the microarchitecture, and then the logic. You're not going below the logic, you're not going above the ISA. Above the ISA is another different course, software programming. Understood? So now let's talk a little bit about the transistor. So this is the first transistor. Have you guys seen it before? No. So this is the first transistor, and then what? But you guys have heard what? You guys know what a transistor is. You've heard it before somewhere. What does it do? What does a transistor do? Transistor. Okay, they are just like your electric switches, right? You can turn your switch on and off, and then once you turn your switch on, what happens? It does like once you turn your switch on, like current flows, right? So it's on, and then once you turn your switch off, you have broken some kind of circuit within your system, and then there's no current flow, right? So your probably light bulb will be off. That is what a transistor do. And then this is the first transistor that was developed in 1947 in the Bell lab or something like that, right? So the transistors within your CPU uses a lot of transistors, right? And then those transistors are probably increasing in number every year. They are increasing in number. So as of probably around 1971, the first Intel 4004 CPUs had only 2300 transistors. 230, only 2300. And then these transistors were known as the MOS transistors, the metal oxide semiconductor transistors. We are not going into that. That is semiconductors. So it has only 2300. And then if we once you jump into the year 2000, if you take Pentium 4, right? The Pentium 4 has about 42 million transistors, right? So it means that something has changed from 1970 what 1 to 2000. You see that the number of transistors have really increased, right? From 23000 to 42 million. Understood? And then it changes every year. And then even if you take for 2000, if you take the Apple M2 Max, it has 67 billion transistors within them. So the number of transistors are increasing continuously. So we have this is how the internal architecture of the transistor looks like. We have a metal, we have an oxide semiconductor, all combined together, right? And then what we are doing here is that we have a gate. We have so this is how it looks like. No problem. This is how it looks like. We have a gate, we have a source, we have a drain. So just like your normal switches, right? You actually put on the gate or you put up the gate. So here in transistors, if you say you are putting on the gate, it means that you are applying some kind of voltage to the gate, right? And then once you apply some kind of voltage to the gate, now electrons or holes will flow from one source to another. Don't worry about that, but it doesn't matter. But once you apply the kind of voltage to the gate, right? Let's say current flows from one end to another. Just understand that, right? You're not going to go so much. So now these are the two type of MOS transistors we have. We have what is known as the NMOS and then the PMOS. Have you guys heard it before? No. Okay. So we have the NMOS and then we have the PMOS. So the NMOS has a gate, a source drain. The PMOS also has a gate, a source, and then a drain. And then typically, as I said, if you take your normal switches, once you don't press the switch, the light is off, right? And then once you press the switch, the lights come on, right? Those are how the transistors work. Now, if you take an NMOS transistor, right, this is how it works. So the NMOS transistor, all we are doing is you are applying voltage to the gate. This is the gate. So you apply some kind of voltage to the gate, and then it will allow source to the drain, apply voltage here, it allows current to flow from the source to the drain, right? Now, a very important thing. Once I apply, let's say a 5 volts here, a 5 volts just means logic 1, right? So if I say logic 1, I mean I've applied 5 volts. If I say logic 0, I've applied 0 volts. Understood? So if I apply 5 volts here, right, what happens? This is like a gate. This, just understand that this kind of closes, right? And then it allows current to flow from here to here. Understood? That is when you apply logic 1. If you apply logic 0, what happens? There's no flow. As easy as that. That's just how the NMOS works. Yeah.
Sir, so with this transistor, we can call this place a base emitter conductor, right?
Yeah, that's BAT, another kind of transistor. But they operate almost the same. Any other question?
So, so all values represent one except zero.
Huh?
All the values, like maybe you've given 5 volts here. So if it's 10 volts, it's still one.
So in the transistors, we only have some kind of, you can't apply just any voltage because they are small devices. They are very, very tiny. So based on the technology they use, you are either applying a 3 volts or a 5 volts. That's why it's stopped. Once you apply any other, that's it, you damage it. So it's either 3 volts or 5 volts. So if you see 3 volts or 5 volts, it just means logic 1. And if you see 0 volts, it just means logic 0. That's all. You can apply something about those values. Understood? So this is just the NMOS transistor. That's how it operates. So we have another transistor called the PMOS transistor, right? So what the PMOS is just the opposite of the NMOS. Right? This is how it looks like, the same way. But we have a bubble here. Have you seen it? So so the PMOS is the opposite of the NMOS. So if I say the PMOS is the opposite of the NMOS, what happens? If I apply logic 1 here, what happens? I said the NMOS, the PMOS and the NMOS are just opposites. They operate opposite, right?
There's voltage supply.
Pardon?
When you apply, it means there's no voltage.
So if I apply logic 1, so logic 1 means 5 volts. So if I apply 5 volts here, there's no flow here. So this gate is open. Now, if I apply 0 volts here or logic 0, that's when this gate will close and then it will allow current to flow through. So you see how they work. Do we understand? Any question? Okay, so that's how they just work. So you apply, one is the opposite of the other. Right. So now we normally use this kind of transistors within our CPU. We use this NMOS and then the PMOS. We use the NMOS and then the PMOS to manufacture our manufacture our CPUs. You know, at first they were actually using the NMOS. They were actually using only the NMOS to manufacture the pieces, I think, at first. And then it was just because the NMOS was easier to handle. The operation of the NMOS uses electrons, right? So don't worry about that. But those electrons were easy to handle than the PMOS. The PMOS uses what is known as the poles. Poles are difficult to handle at that time, right? But now they are using both to construct because the technology has gone so far that they can handle both the electrons and holes easily, right? So now we are using what is known as the NMOS and then the PMOS. So they combine the NMOS and then they combine the NMOS with the PMOS to form what is known as a CMOS, complementary metal oxide semiconductor, right? So they combine the two, NMOS, CMOS, and then that is what they use to manufacture your pieces. Now you need to know how to you need to know how to use this kind of logic gates, this NMOS and PMOS to manufacture simple gates like the AND gates, OR gate, XOR gate, NOT gate, all of that. So let's see how that works, right? So have you guys seen this gate before? This architecture before? Somebody say you have seen it before. You've seen it before. You've seen it somewhere, and you said yes. Right. So if I'm giving an architecture like this, right, this is a typical example of a CMOS because it has the NMOS here, it has the PMOS. Have you seen the PMOS? Then the PMOS is connected to the voltage for 3 volts, right? The NMOS is connected to the ground. This has an input A. It has an output Y. Understood? So it means that it has one input, one output. Have you seen it? So if you are giving a gate like this, and then I ask you to say what type of gate this is, you will know, right? How many gates do you guys even know? Do you know any logic gate? Any logic gate? You know XOR gate, right? You know what again? Eh? NAND gate. Then what? Huh? All gates. Okay, fine. Now, how do you determine a gate? How do you know that a gate is AND gate, OR gate, XOR gate, whatever? Right? So now all you do is that, so if you're giving a circuit like this, what you have to do is draw what is known as the truth table. I think you guys might have seen it before somewhere. The truth table. So this has one input. Right? So I have an input A. And then it has what? One output, right? Y. So input output. So I'll apply logic 0 to it, and I'll apply logic 0 to the input, and look at what happens to the output. And then I'll apply logic 1 to the input, right? And look at what happens to the output. That's how I will know what type of gate it is, or what this entire architecture is doing, right? So now let's go through it. If I apply logic 0 to the input A, what happens? So now we know the basic, we know the how the N MOSFET and the P MOSFET. We said that for the N MOS, once I apply one to it, it will close it. Or let me see what we use. It will close it, right? And then it will allow flow of whatever. And then for the P MOS, if I apply the 0 to it, it will close it, right? Or okay, let's say it will turn it on. Let me put it that way, right? So now if I apply the 0 here, right? So then that 0 here will be 0, and here will be 0, right? Right? So now this 0 will turn this one off. This 0 will turn this one on. So if we study a little bit of electrical the potential differences, voltage is just a kind of potential difference, right? So use this has no voltage, so the voltage here will appear here, or to allow some kind of current to the point that the voltage on top here becomes the voltage here. You understand? Right. So because this gate is closed, this gate is connected to the ground, so this part of the circuit is off. This part of the circuit is on if I apply zero. So if I apply a zero here, this 3 volts will appear 3 volts. So it means that if I apply a zero, Y will be 3 volts, and 3 volts is just logic 1. You see how easy that is? Right? Now if I apply logic 1, what happens? Logic 1 will turn off this transistor, and then logic 1 will turn on this transistor. This part of the circuit is cut off because it's turned off. So this voltage source is no longer connected. Now we are talking about this side. This side is connected to 0 volts, so it will drain any voltage that is here. You know, once you short circuit Once we also a circuit, right? All the wood flows to the ground, right? So this one, a zero will be here. So if I apply logic one to this, to the input of this structure, the output will be what? Zero. Have you seen it? Have you seen how easy that is? Now, you see that, look at what the output is doing. Once I apply a zero, it has kind of inverted the, the input, right? So if I apply a zero, I get a one. If I apply a one, I get a one. That's inverted it. So we call this gate an inverter. That's what we call it, inverter. Is it or inverter or a NOT gate? This is just how it looks like. I think you have seen it before. This, and then this is how it works. So this, once I do something like this, it means that this internally is made up of this. But I don't. But we usually want to make it simple, so we just draw it. Like, so once you do it like this, it means that the internal architecture is like this. Understood? Right. So this is a NOT gate. So all of this is just trying to explain the NOT gate. So now a more complex gate. What is this gate? So if I want to know what this gate is, I simply have to do the exact same thing I did with this, with the NOT gate. So now here we have two inputs, A and B. Right. So instead of just A, I will have A and B. I have A and B, and then with A and B, I have to apply 0, 0, 0, 1, 1, 0. Right. So this is the output Y. So I have A and B as input. I apply 0, 0 to the input, 0 to input A, 0 to input B, and then I go through the circuit again. Some will be turned on, some will be turned on, some will be cut off, some and stuff like that. And then I found out what the output is. Right? So should I continue or you guys want to go through it? So now, but you have to pay attention that the N mosses. Have you seen how the N mosses are? The P mosses are arranged. They are arranged in parallel, right? Have you seen it? The P mosses, P1 and P2. They are arranged in parallel. They are always arranged in parallel. Then the N mosses are always arranged in series, right? So now here, if I apply 0, 0, P1 will be on, P2 will be on. So you can actually go and sit down and go through this and see how it works. But this is what the truth table looks like. So it will be the output will be 1, 1, 1, 0. And then what kind of gate is this? Who knows? If A and B is 0, 0, the output is 1. If A and B is 0, 1, the output is 1. A and B is 1, 0, the output is 1. If A and B is 1, 1, the output is 0. What kind of gate is this? A simple NAND gate, right? Now, so the NAND is a what? Is not AND, right? So if I have this circuit here, if this circuit is for NAND, how do I combine transistors to form an AND gate? What must I do to this circuit to make it an AND gate? Who knows? Because this is a NAND gate, and the NAND is just the opposite of an AND, right? So what must I change in this circuit to make it an AND gate? Who knows? Just little think it's more. So the NAND gate is a not AND, right? So what is AND gate? So if this is the circuit for AND, so all I have to do is I have to connect. You see the output there, right? have to connect an inverter to the output, and then it will just invert all these values for me, and then it will be an AND gate. It's as simple as that. Understood? You understand? And then this is, you guys know, this is a symbol for the NAND gate. You have a bubble, and then the AND gate is just there's no bubble there, right? All right. So if I want an AND gate out of the NAND gate, I just connect the inverter will just do that, and then it will invert all the output for us, and then it will just turn it into an AND gate, right? So we have the NOT gate. That's what we looked at. We have looked at the NAND gate, and then this is the AND gate. And then all of them have their truth table. And I believe by now you guys can draw the truth tables for all of them. Do you understand? Okay. So now the most there is a law in computing known as the Moore's law, right? And then the Moore's law states that the number of transistors within a computer system will increase or will double every 2 years, right? And then this, I think they started in 1965, right? There was an engineer called Moore, and then he predicted in 1965 that the number of transistors within a chip, right, will double every 2 years. And then his predictions have been true for a very long time, from 1970 up to about 2005. So because technology is actually changing, right? Technology is getting better and better. So that's why they're able to increase the number of transistors within a single chip. So you take a single chip, every 2 years, the number of transistors within that chip double, right? So how is it doing that, right? So now all they're doing is that they're making the chips smaller. They're making the transistors smaller. So if you take a transistor size, once you take probably the NMOS transistor, right, we have this portion is called the channel, right? Or what they're doing is that they're making the channels smaller so that they can pack more into a single chip, right? It's as simple as that, right? But now, once you get to 2005, the number of transistors have actually become stable. They can't increase it anymore on a single chip because they are getting into some issues. Now, they've seen that once you are making the channel smaller, they've gotten to a stage where they cannot make it smaller anymore because there will be some kind of leakage current, right? And then also, there's another issue. If you pack so many transistors, because the transistors produce heat, they are finding it difficult how to handle the heat produced. So once you are packing transistors, you know that you are producing more heat, right? So now from 2005 onwards, the number of transistors have become stable. So the Moore's law that says that the number of transistors increase every 2 years is dying out. Understood? Right. So that's the end of the first one. Any question? It's as simple as that. Any question?